This is tutorial 8 linear algebra question 10. We have the original question here, A, and I have added a new question, B. Let's answer this question. A is square and invertible. That means A has A inverse. Find the singular value decomposition of A minus 1. If A is decomposed using SVD, we have U sigma V transpose. So if this is a square n by n matrix, this guy would be an n by n orthogonal matrix, meaning U transpose U is U transpose is I. This is also an orthogonal matrix. V transpose V is equals to I. V transpose equals to I, because this is also an n by n matrix. The singular value decomposition means that the sigma is a diagonal matrix of n entries in the diagonal that are non-zero, because A is invertible. Now we make use of the fact that U and V's are orthogonal matrix. Therefore, A inverse is actually nothing but V sigma minus 1. Inverse of a diagonal matrix is very easy. It means all the diagonal entries are reciprocated, and U transpose. Let us see why this is true. A times A inverse is equals to U sigma V transpose V sigma inverse U transpose. This will cancel because this is I. This will cancel because, again, the diagonal entries multiplied by its inverse is nothing again but I, and this is again I. Therefore, this is equals to I. This is for the right hand side. We can also try on the left hand side, because this is the inverse, and this is V sigma inverse U transpose multiplied by U sigma V transpose. Again, when we start to open up the bracket, this is the identity, this is the identity, this is again identity, and therefore A can be multiplied by its inverse on the left hand right hand side by using the SVD decomposition U sigma V transpose, and we see this is the answer. That is, I repeat, the inverse of A in the SVD is this matrix over here. So this is 18A. We now turn our attention to 18B, where we want to generalize where A is no more a square matrix, it is a rectangle matrix. Let's assume that we have a tall and thin matrix m by n, and however rank is r. Therefore, what happened is that when rank is r is less than n, implying that we have dependent column. We only have r independent column, and this is not enough for all the columns. So find pseudo inverse of A. So the pseudo inverse of A has this notation A plus. So what is A plus? Let us now proceed. We now write A equals to U sigma V transpose first, and we denote the size. This is a m by n matrix with rank r. It means that we have U1, U2 until Um, and each of the columns of U is dimension m. So we have a m by m matrix. This is square. U transpose U would be still identity. However, what is important is that only the first R columns are important, because later on you will see that the the singular values of associated with sigma, only the first R singular values are non-zeros. Okay, Right, so we call the first R column UR. We also is interested to find out more about V. What about V? The matrix V is also represented as columns. V is n by n, because if this U is m by m and sigma is m by n, then V transpose must be n by n, such that we'll get a m by n matrix. Now we'll write again, this is V1, V2 until Vn. Again, what is important is that only the first R columns of V is important, because as before, only the first R eigen or singular values are non-zero. We call the first R column VR. We also call the square singular matrix sigma R to be the only consisting of the first R singular values that are non-zero. Then we can now find A plus, the pseudo inverse of A. The details you can read from the book, but A plus is VR, DR minus 1, UR transpose. The reason we're using only the R entries is because only the R singular values, the first R singular values are non-zero. So we are only capturing the first R singular vectors from both the left hand side and the right hand side to get the pseudo inverse. That's it. Thank you.